Hello, so in this video I'll be working through a harder vectors question that might come up, that is the sort of style that would come up in paper 4. So we're given a trapezium OPQR and O is the origin, and they've given us a few vectors, and now they've told us that the magnitude of RQ is 3/5 the magnitude of OP. And they've given us OP as the vector O to P as B. So therefore, R to Q is 3/5 of that. So this is 3/5B. So now they're asking us to find P to Q in terms of A and B in its simplest form. So to get from P to Q, we need to, with the information that we're given, we need to firstly go from P to O, and then O to R, and then R to Q. So essentially, PQ is equal to P to O plus O to R plus R to Q. So PQ is equal to PO is negative B, because since O to P is B, O to P is B, but if we're going in the opposite direction, it's negative B. And then O to R we already given as A, so minus B plus A. And then R to Q, we just worked out R to Q is 3/5B. So therefore, P to Q is equal to 2/5, negative 2/5B plus A, or A minus 2/5B. So that's our answer for that one. A minus 2/5B. Okay, so for the second part, when PQ and QR are extended, they intersect at W. Find the position vector of W. So the position vector is essentially from the origin to W. So what they're asking us here is from the origin, which is O, to W, which is OW. So they're asking us what the vector OW is. So let's firstly extend the lines PQ and QR, and they intersect at W. Sorry, PQ and OR, when the lines PQ and OR are extended. So something like this. And this would be the point W. So now, the way to solve this is to identify similar triangles. So if we treat these as so now, if we treat this as a triangle, we see that WRQ is similar to the triangle WOP. It's similar because it shares a common point W, a common angle W. So it's W right here is common in both triangles. So what we're essentially saying is that WRQ is similar to triangle WOP. So firstly, we've got that the angle RQW is equal to the angle OWP. Sorry, the angle RWQ, this angle right here, is equal to the angle OWP, since it's the same point W. And also, we've got that this angle right here, angle WRQ, is equal to angle WOP, because they are corresponding, because these two lines are parallel since it's a trapezium. So QR is parallel to OP. QR is parallel to RQ is parallel to OP because it's a trapezium, and also because they've given us this piece of information, which shows us that R to Q is 3 over 5b, and since they both have a vector of b time multiplied by a scalar, they both are parallel. So that means that angle WRQ is equal to angle WOP. They're corresponding, and similarly, WQR is equal to WPO, since the lines RQ and OP are parallel. WQR is equal to WPO. So now we have three angles. So this is proving similarity by angle, angle, angle. So now we can work with that information. So the scale factor is, well, we know that R to Q is 3 over 5b. So therefore, the scale factor the scale factors can be calculated by doing OP, which is the length of the bigger triangle, the base length of the larger triangle, divided by the base length of the smaller triangle right here. So OP over RQ, and we know that OP is equal to B, that's given to us. That's equal to B over, and RQ is 3 over 5B as we calculated it here. So 3 over 5B. So the B's cancel out, and we're left with 5 over 3. Therefore, we've got OP to RQ as being 5 to 3. So therefore, now that we have one pair of sides with their ratio, we know that since it's similar, these two triangles are similar. We have the ratio of all the sides as 5 to 3. So essentially RW is 3/5 the length of OW. It's 3/5 the length of OW. Since RQ is 3/5 the length of OP, and they're similar triangles. So therefore, let's write that down. WR is equal to over WO is equal to 3 over 5. Right? It's equal to 3 over 5. But we know that WO is equal to WR plus RO, which is equal to WR plus A. Sorry, let me rephrase this right here. So RW is 3/5 the length of OW. RW is 3/5 the length of OW. And we know that OW is equal to OR plus RW, which is equal to, therefore OW is equal to OR is given to us as A plus RW. So now let's just substitute this value in for OW here. So therefore RW equals to 3 over 5 A plus RW. So RW is equal to 3 over 5A plus 3 over 5 R to W. So So now if we multiply both sides by 5, we get 5 times magnitude of RW is equal to 3A plus 3 times the magnitude of RW. So now 2, if we subtract 3 R times R to V, to R to W from both sides, if we subtract 3 times the vector R to W from both sides, we get 5 R to W minus 3 R to W, which is 2 times the vector R to W is equal to 3A. And therefore in the end we get RW is equal to 3 over 2A if we divide both sides by 2. So now we have R to W is equal to 3 over 2A. So therefore the position vector is O to W. We've already determined that. It's from the origin O to W, which is, and we know that the vector OW is equal to A plus R to W. We've shown that here. The vector O to W is equal to OR plus RW, which is equal to A plus R to W, since vector O to R is A. Therefore, we can now substitute this value in here into this equation here, and we obtain that the position vector of W, OW, is equal to A plus 3 over 2A. And therefore, OW is equal to 5 over 2A. And that's our answer. That's our answer, 5 over 2A. That's the position vector of W. So it's we showed that this one is 3 over 2A, and therefore the position vector is A plus 3 over 2A, because we're going from O to R, which is A, and then further from R to W, which is 3 over 2A. So if you add them up, it gives you 5 over 2A. So yeah, that's how you solve these more complicated vectors questions, where they involve extending lines and intersections. So yeah, I hope that was helpful. If it was, please like, share, and subscribe, and comment any other problems you'd like me to go through. Thank you very much.